Good afternoon. This file contains the pre-lecture notes for class on Thursday, October 31st. The relevant reading is the conclusion of the Carey Chapter 10, sections 10.11 through 10.16. In this pre-lecture, we're going to discuss the reactions of conjugated dienes. These will be addition reactions of alkenes as we've seen before, except the functional group of a diene acts as one unit and not as two individual alkenes. Because of this, there are two different types of addition reactions that can happen at a conjugated diene. This is direct addition, in which the electrophile adds to a single pi bond in the conjugated system, or conjugate addition, in which the electrophile adds either to the 1,2 or the 1,4 carbons in the system. Related to this, we will discuss thermodynamic products and kinetic products. Thermodynamic products are those products that form which are more thermodynamically stable. Kinetic products are those products that form faster but are not necessarily as stable as the thermodynamic product. You have already seen these two different types of products in many of the reactions we've looked at so far this semester. Okay, so remember the three different types of dienes we've discussed on Tuesday: isolated dienes, conjugated dienes, and cumulated dienes. Isolated dienes, since they are independent, the double bonds react completely independent of one another. Conjugated dienes, however, act as one single functional group unit, and the reactivity pattern requires us to think of the conjugated diene system as its own functional group. Cumulated dienes are a specialized topic that we won't get into this semester, but you'll follow up in 234 on their reactions. So, we'll begin our discussion of the electrophilic addition of conjugated dienes by looking at the first step in the mechanism. In any case where you have the electrophilic addition of a conjugated diene, you will always add the proton to the end of the diene system. So as we can see here, one of the double bonds in the conjugated diene attacks the proton and selectively adds that proton to the terminal end of the diene system. The leaving group, which is kicked out in the previous step, then comes in to attack the carbocation. Note, you do not add the proton to the internal carbons of the conjugated diene. The reason for this is that by adding the proton to the terminal end of the conjugated diene, we generate an allylic carbocation that has multiple resonance structures. These multiple resonance structures make the allylic carbocation much more stable than it would be were it a tertiary carbocation that is not allylic at the terminal end of the original diene. Given the observation that the proton in the electrophilic addition of a conjugated diene must add to the end of the conjugated diene functional group, we can anticipate the different types of products that would be produced from any compound that contains a conjugated diene. Here on this slide, we see the example of the addition of hydrochloric acid to 1,3-cyclopentadiene. Can you anticipate which of the two products will be formed in excess in this reaction? If you guess that it's the product on the bottom left, you are correct. This product involves the addition of the hydrogen atom to the end of the conjugated diene system with subsequent attack of the carbocation by the chloride ion. Let's look at the mechanism. So in the first step, one of the pi bonds in the conjugated diene attacks the proton, which removes the leaving group. This generates our allylic carbocation through the addition of the hydrogen atom to the vinyl carbon that's at the end of the conjugated diene. The protonation at the end gives an allylic carbocation that has resonance structures which is more stable than a carbocation that does not have allylic resonance structures. Notice that the two resonance structures that are possible involve the interchange of the carbocation with the double bond across three different carbons, thus delocalizing the positive charge across all of the carbons. In the next step of the mechanism, the chloride nucleophile can return to attack the carbocation. In this case, there are two possible carbocations that can be attacked. In the top pathway, the carbocation formed from the original addition of the hydrogen atom to the conjugated diene is attacked directly to form the chloride. In the bottom pathway, we see what happens if the chloride anion attacks the resonance structure of the original compound we generated upon electrophilic addition. In both cases, notice that the product is the same regardless of where we attacked with the chloride anion. As always, if you're not sure if these two compounds are the same, apply the IUPAC naming system and you'll see that they're both named 3-chlorocyclopentene. The attack of the nucleophile at each of the different carbon atoms in the resonance structures is known as 1,2 addition versus 1,4 addition. 1,2 addition involves electrophilic addition across two vinyl carbons that are in the same alkene in the conjugated diene. 1,4 addition results from subsequent attack of the nucleophile in the second step of the mechanism on the resonance contributor. Let's look at another example that does not involve a cyclic structure. Here we'll look at the addition of HBr to 1,3-butadiene. Electrophilic addition can be observed at both the 1,2 and the 1,4 positions. It turns out that the ratio of 1,2 to 1,4 addition is a function of the temperature at which the reaction is run. So, the product on the left is formed much faster than the product on the right. The reason for this is because the allylic carbocations react with the nucleophiles preferentially at the carbon that bears the greater share of the positive charge. Notice in the bottom the two different resonance contributors that produce each of these products. The structure on the bottom left is a secondary allylic carbocation. The structure on the bottom right is a primary allylic carbocation. Because the structure on the left is more stable, it is formed much more faster than the structure on the right. In contrast, however, the product on the right is a more stable product than the product on the left due to the fact that it has a more highly substituted double bond. So, to return to the previous slide, notice the structure on the left forms faster because the carbocation intermediate is more stable. However, the structure on the right forms slower yet is more stable because it's a more highly substituted double bond. We are able to manipulate the relative ratio of each of the two products by manipulating the temperature of the system. At lower temperature degrees, the product that includes the more stable carbocation will form faster than the product that results from the less stable carbocation. At higher temperatures, we will produce the product that results from the less stable carbocation because this produces the more stable thermodynamic product that is the more highly substituted double bond. Yeah. In this example, the 1,2 addition product is formed faster and the 1,4 addition product is more stable. Note that this will not always be the case and you will need to inspect the relative number of substituents around each of the alkenes to determine which product is more stable, as well as the relative number of alkyl substituents around the intermediate carbocations to determine which product forms faster. Controlling the relative ratio of each of the 1,2 and 1,4 addition products is known as kinetic control versus thermodynamic control. Kinetic control is controlling a reaction such that the major product is the one that's formed at the fastest rate. In contrast, thermodynamic control involves producing a product that is more stable. Once again, let's look at the intermediate carbocations that result from the addition of HBr to 1,3-butadiene. After attack of the proton by the pi bond, we produce two resonance contributors that are as follows in red. One of these resonance contributors will lead to the 1,2 addition product, the other will lead to the 1,4 addition product. On this slide, I've shown the relative differences in activation energy for formation of the 1,2 and the 1,4 addition products. Remember that the two resonance contributors are both different forms of the exact same molecule. They are not two different molecules. As such, each of these forms has the exact same energy plotted on the reaction coordinate diagram. Due to the stability of the more highly substituted carbocation, the activation energy to produce the 1,2 addition product is much lower than the activation energy to produce the 1,4 addition product, which results from the less stable resonance contributor. Note, however, once again, in this case, the 1,4 addition product involves a more highly substituted double bond, which means that the final product is more stable despite the fact that it took more energy to make that final product. let's look at an example of kinetic control applied to a new molecule. Here we'll examine the addition of hydrogen chloride to 2-methyl-1,3-butadiene. This is a kinetically controlled reaction that gives one product in much greater amounts than any of its other isomers. Can you figure out what this kinetic product is? The way to determine this is to look at the addition of HCl to each of the double bonds in the conjugated system independently to determine which will produce the more stable carbocation. Think mechanistically to accomplish this. First, you must protonate one of the two double bonds. Remember, the proton must always be added to the end of the diene system. In this case, you have two termini of the diene system, and the question put to you is, which of these ends will the proton be added to? For kinetic control to be followed, we must produce the most stable carbocation possible. Thus, you'll want to add the hydrogen atom to the end of the double bond that is included in the conjugated diene, which produces the most stable carbocation intermediate. Let's consider two options, adding the proton to either end of the double bonds. On the left, we see we're going to add the proton to the alkene on the right side of the molecule. On the left, we'll look at adding the proton to the alkene on the left side of the molecule. Remember, regardless of which alkene we're working with, the proton can only be added to the end of the conjugated diene system. You cannot add the proton to the vinyl carbon that is internal to the conjugated diene system. The results of this first step in the mechanism on the left side would produce the following resonance contributors. One resonance form is a tertiary carbocation, the other is primary. Both of these resonance contributors are allylic. On the other side, we see that the first step in the mechanism also produces a set of resonance contributors. In this case, one resonance form is a secondary carbocation and the other one is a primary carbocation. In both cases, these two resonance contributors are allylic. Looking at both sides of the slide, can you determine which resonance contributor set has the most stable carbocation? If you guessed it's the one on the left, you're right. In this case, we have a primary carbocation that is allylic as well as a tertiary carbocation that is allylic. As such, this carbocation resonance contributor is the most stable of the two. Over here, we have only a secondary carbocation resonance contributor, which is not as stable as a tertiary carbocation intermediate. Kinetic control of this reaction involves the mechanism on the left side because it produces the most stable carbocation intermediate. Given that we've now determined that the proton adds to the end of the conjugated diene system, including the vinyl carbon on the right side of the molecule, we can decide what are the 1,2 and the 1,4 addition products that will result of attack of the chloride nucleophile to each of the carbocation resonance contributors. Remember that the major product that results from kinetic control involves attack of the nucleophile in the most stable carbocation intermediate. As such, we should produce the tertiary allylic chloride as our major product under kinetic control for this molecule. In contrast, attack by the chloride anion on the primary carbocation resonance structure would produce our minor product. That would be the thermodynamic product because it would have the more highly substituted alkene. A second type of reaction that's important for conjugated dienes is called the Diels-Alder reaction. This reaction involves the collision between a conjugated diene and an alkene. The alkene is known as a dienophile due to the fact that it acts as an electrophile in the Diels-Alder reaction. The product of a Diels-Alder reaction always includes a cyclic structure. In cases where a conjugated diene combines together with an alkene, we produce always a cyclohexene structure. In cases where the conjugated diene combines together with an alkyne, we create a cyclohexadiene structure. The mechanism for this reaction involves three important features. First, the mechanism is concerted. That means it happens in one step only. This is a cycloaddition reaction in which we take two acyclic structures and form a cyclic structure upon completion of the reaction. This is also a pericyclic reaction, which means that the mechanism involves the formation of the cyclic structure through a cyclic transition state. This slide shows the mechanism for a Diels-Alder reaction. The reaction involves the movement of all three pi bonds between the conjugated diene and the dienophile. Again, the transition state is pericyclic. As bonds are breaking and being formed, they assume a cyclic structure. The product of the reaction is a cyclohexene in this case. A question arises about what makes a reactive dienophile. In all cases this semester, we've seen that alkenes act as nucleophiles due to the fact that they attack electrophiles in addition reactions. In order to make an alkene a dienophile, or a good molecule that can be attacked by a conjugated diene, we need to place electron withdrawing groups as substituents onto the vinyl carbons in the double bond. Typically, electron withdrawing groups that you'll see this semester are carbonyls and cyanide groups. These two groups draw electron density towards them away from the double bond in the dienophile, thus allowing it to be attacked by the conjugated diene in the Diels-Alder mechanism. Let's take a look at an example of a Diels-Alder mechanism. You can recognize a Diels-Alder reaction as any reaction that involves two reactants that include a conjugated diene, as well as an alkene dienophile that has an electron withdrawing group attached directly to one of the vinyl carbons. Remember, in some cases, the double bond may in fact be a triple bond. Alkynes can also act as dienophiles in Diels-Alder reactions. The mechanism is shown in the box down here in the bottom left hand of the slide. Notice the pericyclic transition state that leads to the formation of the cyclohexene product. Here's another example of a Diels-Alder reaction. Once again, we have a conjugated diene combined together with an alkene that has electron withdrawing carbonyls coming off of it. Don't be misled by the fact that this alkene is in a cyclic structure. Notice there's an alkene here with two carbonyls bonded directly to it. Remember, those carbonyls are electron withdrawing groups, which makes this alkene a very useful dienophile for a Diels-Alder reaction. Once again, our mechanism involves a pericyclic transition state and formation of a cyclohexene product. Notice that the substituent coming off of the original conjugated diene remains exactly where it was. All that moves in terms of electrons in a Diels-Alder reaction are the pi bonds that are in the conjugated diene as well as in the dienophile. Here on this slide is an example of an alkyne used as a dienophile. Once again, I recognize this as a Diels-Alder reaction because we have a conjugated diene being combined together with a triple bond that has two carbonyl groups or two electron withdrawing groups attached directly to those carbons that are in the triple bond. The product of the reaction between a conjugated diene and an alkyne is not a cyclohexene, however, it is a cyclohexadiene. Remember, the mechanism involves the movement of three pairs of pi electrons to form the cyclic product. In this case, that leaves behind one pair of pi bond electrons in the original triple bond to produce a cyclohexadiene. It's important to note that Diels-Alder reactions are stereospecific. This means that the geometry of the dienophile in the starting material will determine the relative stereochemistry of the cyclohexene product. Diels-Alder reactions always involve syn addition to the alkene. This means that in cases where you're starting with an E alkene as your dienophile, you will produce a trans cyclohexene product. In cases where you are using a Z alkene dienophile, you will produce a cis cyclohexene product. Thus, the cis-trans relationship of substituents on the starting alkene determine the cis-trans relationship in the cyclohexene product. Let's look at an example of this. Notice once again, I can tell that this is a Diels-Alder reaction because it involves the combination of a conjugated diene together with a dienophile. This dienophile is an alkene that has two electron withdrawing groups attached to it, both indicated with color. Note that this is an E geometric isomer in which both substituents are on the same side of the alkene. As such, I should predict that the product of this reaction will be a cyclohexene structure that includes both of the original substituents on the alkene on the same side. It should be a cis cyclohexene product. Indeed, The only product that's produced from this reaction is the cis-cyclohexene product. Don't forget, because this is a stereospecific reaction involving the syn addition of the electrophile to the conjugated diene, you can also produce the enantiomer if the electrophile approaches the diene from the opposite side. Here we have an example of a Diels-Alder reaction that involves a transalkene. As predicted, the geometry of the original alkene determines the stereoisomerism of the cyclohexene. With that, we conclude our review of 1,2 and 1,4 additions to conjugated dienes, as well as the Diels-Alder reaction. As always, make sure you review the relevant reading in the Carey textbook and come to class prepared to apply what you've learned.